Welcome to The Explainer. Today, we're going to follow a single sunbeam on its incredible journey. We'll track it all the way from space, see how we capture it with some really cool tech, and watch it become the power we use right here on Earth. So, here's our game plan. We'll start with the sun's energy itself. Then, we'll look at how we actually catch that sunlight. We'll check out the two main ways to do it, the everyday version and the powerhouse version. After that, we'll see how all that heat becomes electricity, and we'll wrap up by looking at the big challenges this tech faces.
Okay, so let's dive right in at the source. Before we can talk about capturing sunlight, we have to ask, what is the sun actually sending us? Because, it's a whole lot more than just the light we see with our eyes.
So what we're dealing with here is called solar radiation. It's basically pure energy traveling 93 million miles through the vacuum of space just to get to us. You can think of it as the raw fuel for this entire process. It's this energy that we're going to turn into useful stuff like heat and electricity. But here's where it gets interesting. That energy doesn't just arrive perfectly intact. Our atmosphere is like a bouncer at a club. It reflects some energy back into space, absorbs some, and the stuff that gets through is actually split into two very different types by the time it reaches the ground.
And this difference is everything. You've got direct radiation. That's the intense, focused sunlight on a clear day that gives you sharp shadows. Then you have diffuse radiation, which is scattered by clouds and haze. It's weaker, more spread out. Why does this matter so much? Well, the type of radiation you're getting dictates what kind of solar technology you can even use. It's a fundamental fork in the road.
All right, so the sun's energy has finished its long journey and is now hitting the Earth. So, now what? How do we actually grab it? It's not like you can just stick a bucket out in the yard, right? We need some pretty smart technology to do the job.
And the hero of this story is a device called a solar collector. The best way to think about it is as a super efficient heat trap. Its one and only job is to absorb as much solar energy as it can, and, this is the important part, to not let that heat escape. It's all about maximizing absorption and minimizing loss. Okay, so if the goal is just to capture heat, how do you do it best? Well, it turns out there isn't just one answer. It really depends on what you need that heat for. Are you just trying to warm up your swimming pool, or are you trying to power an entire city? Those are two very different goals, and they lead to two totally different strategies. So let's start with the one you've probably seen before. This is the everyday collector, the kind of thing you might spot on a rooftop in your neighborhood.
This thing is basically a mini greenhouse in a box. It's so clever. Sunlight shines right through the glass on top. It hits that dark plate inside, which soaks up the energy and gets really hot. But the heat can't easily get back out through the glass, so it gets trapped, heating up the water or fluid that's flowing through those pipes. Simple, but super effective. And if you look at the materials, everything has a purpose. That absorber plate, usually made of something like copper that heats up fast, that's your workhorse. The glass on top is like a one-way door for heat, and then you've got insulation packed around the back and sides to make absolutely sure all that precious heat stays put.
Now here's the real genius of this design. It can use both direct and diffuse sunlight. That means it still works on cloudy days. That's huge. Because it's so simple and relatively cheap to make, it's absolutely perfect for those everyday jobs, like making sure you've got a hot shower or heating the backyard pool.
But of course, there's a trade-off. This simple design has its limits. It just can't get hot enough to do the really heavy lifting, like generating electricity for a power grid. So it's fantastic for low-temperature stuff at home, but you're definitely not going to power a city with these.
Okay, so what if you do want to power a city? What if you need incredibly high temperatures? For that, you need a whole different beast. It's time to talk about the power collectors, where we're not just trapping sunlight, we're concentrating it.
Forget passively trapping heat. This is way more aggressive. Think about using a magnifying glass to focus sunlight on a single point. That's exactly what's happening here, but on a massive scale. These curved mirrors collect sunlight over a huge area and focus all of that energy onto one superheated tube.
And you can bet the materials have to be up to the job. We're talking about ultra-reflective mirrors and special coatings that can handle insane temperatures. We're talking over 500 degrees Celsius sometimes. They even have to use exotic stuff like molten salt just to move and store all that intense heat.
So what's the big payoff for all this complexity? It's simple. Incredibly high temperatures. And that high-grade heat is the magic ingredient you need to do things like boil water into high-pressure steam, spin a massive turbine, and generate electricity on an industrial scale. This is how you power a grid.
But again, there's a catch. Remember how the flat plate collectors worked on cloudy days?
Well, these absolutely do not. They need that clear, direct sunlight to work. A little bit of cloud cover can basically shut the whole operation down. Plus, as you can imagine, building fields of giant mirrors is not cheap.
All right, we've got our system. We've used these massive collectors to create some seriously intense heat, but we're not done yet. How do we get from a pipe full of super hot molten salt to you being able to turn on your lights? Let's connect the dots.
This diagram lays out the whole process. That solar collector field we just talked about, that's just step one. All the heat it gathers gets sent on a journey, and the entire goal of this journey is to turn that thermal energy into physical motion.
It really is just a brilliant chain reaction. Okay, follow me here. Step 1, sunlight heats up a fluid. Step 2, that superhot fluid is used to boil another liquid, something that boils easily, creating a ton of high-pressure gas. Step 3, that pressurized gas is blasted at a turbine, making it spin like crazy. And finally, step 4, that spinning turbine is hooked up to a generator which produces electricity. So you go from sunlight to heat to pressure to motion to power. Just like that.
So, this technology is obviously incredibly clever and powerful, but let's get real for a second. It's not a magic bullet. There are some major real-world challenges we have to talk about.
When you boil it down, the two biggest problems are space and time. First, space. Solar energy is spread out, so to collect enough of it to be useful, you need a huge amount of land for all those collectors. And second, time. The sun moves across the sky all day, and it disappears completely at night. That means you need complex tracking systems to follow it, and, crucially, some way to store that energy for when the sun isn't shining, which can get really expensive.
Which leaves us with a really interesting question for the future. Yes, the challenges are real, but technology doesn't stand still. As we get better at making cheaper materials, and as energy storage gets more efficient, you have to wonder, could these vast, empty deserts one day become the power plants that run entire